All right, in this video, I'm going to go through the applications in the hypothesis test section. And as I did in the last video, I've got the answers here along with illustrations, but we can go through them so you understand clearly. Uh, Last time we did the 5 steps, but now we're going to apply those 5 steps to this application down here that says a phone industry manager thinks that customer monthly cell phone bills have increased and now average over $52 per month. The company wishes to test this claim. Assume that the population standard deviation is equal to 10. Suppose a sample is taken with the following results. N is equal to 64. The mean is 53.1. Calculate the critical and computed value at a 5% level of significance and determine the decision rule. Okay, so let's go up to our first step. It says state the null and alternative hypotheses. Well, the null and alternative are going to be defined by the narrative. And what we want to look for is a equality or inequality. Take a look. It says cell phone or phone industry manager thinks that customer monthly cell phone bills have increased and now average over 52 per month. This is important. The fact that it says over 52 tells you you do not have an equality, which means this is going to be placed in the alternative. The alternative is that the population mean is greater than 52, right? Over 52 per month. Now, by default, that defines your null. If the alternative is greater than 52, the null must be less than or equal to 52. So get in the habit of doing that with your narratives. First find either the equality or the inequality in the narrative and then put it in its proper place, and then by default find the other. All right, so we've done that now. Now let's specify the desired level of significance. Well, it tells us that we need a 5% level of significance right there. Okay, so we just write that in, right? Or circle at 5%. 3, determine the critical value, either z or t. Now in this particular case, we know what the population standard deviation is. It gives it to us. It's 10. So because we know that, we would use z, not t. Next, we want to actually calculate it. And to do that, we're going to illustrate our normal distribution here. And we want to find whether this is an upper or lower tail test. The easiest way to do this is to look at your alternative hypothesis. And if we're looking for a population mean that is greater than, you have a right tail test. If this were an alternative that was less than, you'd have a left tail test. Okay, that's just a quick, easy way to do it. So we have a right tail test. And we know in this right tail, we're going to have 5% because that's our level of significance. So this would be 5%. Now let's find the z-score that corresponds to that. Well, recall from before that to find a positive z-score, you find in your table the probability from the left tail all the way to that particular point. And if 5% is in this tail, then we would find the z-score that corresponds to a probability of 95%, right? Just like before. So let's go to our z table here, okay, and look for 0.95. Okay? And it looks like we've got either this one or this one. Let's use 1.65 since it's the one there. So we have 1.65 as our critical z. Okay? Now, this 1.65 defines the rejection region. So if we take a sample and we get that sample lying more than 1.65 standard errors above the mean, then we know that we have a rejection. If, in contrast, that sample lies less than 1.65 standard errors above the mean, then we know that we do not have a rejection. We would fail to reject. Okay. Next step is to actually calculate the z value, what we call the computed value. And we've got our critical value. Now we find the computed value. And to do that, we use this formula here. We take our sample, which was 53.1, right? Find it down here. Says the mean was 53.1. And we subtract that from our hypothesized population mean, 52. And then we divide that by our standard deviation, 10, over the square root of our sample size, 64. And if you do this correctly, you should get 0.88. Okay? Now it's a positive because the actual sample value is greater than the hypothesized mean, right? X bar is greater than the hypothesized population mean. So where are we in our diagram? Well, we're right here, right? 0.88 z-score is our computed value. We then compare that to the critical value of 1.65 and determine whether we should reject or not reject. Well, we're not in the rejection region. We're at 0.88, which means this particular sample mean only lies 0.88 standard errors above the hypothesized population mean. It would need to lie 1.65 or more in order for us to reject it. So it's just not far away enough from the hypothesized population mean for us to reject it. So we do not reject. Okay? In other words, it is possible that our null hypothesis is accurate, that in fact the mean is less than or equal to 52. Okay, now let's move on to the next one. It says test the hypothesis that the average number of TVs in US households is less than 3. Your sample consists of 100 households with a mean of 2.84 TVs. You know the population standard deviation to be 0.8. You desire a level of significance of 0.05. We start with step 1, find our null and alternative hypothesis. And again, we look at the narrative. It says test the hypothesis that the average number of TVs in US households is less than 3. The fact that it says less than tells you that we have a alternative here, right? Because there's no equality there. Less than does not have an equal in it. So that defines our alternative. The population mean is less than 3, which by default creates our null. Population mean is greater than 3. Step 2, find the alpha, level of significance. We know it's 0.05, right? Gives it to us. Third step, find the critical z. To do this, let's draw our diagram and let's determine if this is a left or a right tail test. We'll recall from before that we look at the alternative hypothesis, and if the mean for the alternative is less than, it's a left tail test. So we shade in this area, and that left tail is going to have 5% in it because that's our level of significance. That's our alpha. From there, we go to the z table and find the proper z-score. And recall that to find a negative z-score, we find the probability from the right tail all the way to this point, which is 95%, right? 0.95, because 5% is in this tail. So we're looking for 0.95. 0.95, we can use 1.65 right there. And that's what we have here, right? Negative 1.65. So that defines our z alpha, aka z critical. Next thing we need to do is find our computed z. To do this, we use our formula. We know that the sample mean is 2.84 TVs. That's there. We find how far that is from the hypothesized population mean, 3, 2.84 minus 3, and then we divide that by our standard error, which is our standard deviation for the population, which we know population standard deviation it gives to us right there, 0.8, divided by the sample, which is 100 households. Okay? And then that's the square root of the sample. If you do that correctly, you should get a negative 2. So that's our computed value. Compare that. We get a computed value way down here in this tail. But our critical value is here. which means we're in the rejection region. So based on the sample with a mean of 2.84, it looks like we're going to have to reject our null and accept the alternative. We're going to have to reject the idea that the population mean is greater than or equal to 3 and accept that it is in fact less than 3. All right, so that's the process. Let's keep going. It says a national perfume manufacturer claims that the cost of processing a sales order is $12.50. In order to test this belief, it obtains a random sample of 40 orders and finds the mean processing cost is $12.75 with a population standard deviation of 0.5. Test the claim at the 1% level of significance. Let's do the steps. First step, create our hypotheses. Well, look at the narrative. The perfume manufacturer claims that the cost of processing a sales order is $12.50. That's an equality. So we've now defined our null hypothesis that the mean is equal to $12.50, which by default gives us an alternative where the mean is not equal to $12.50. Our alpha level of significance is given at 1%. So we've got that there. Step 3, let's find our critical Z. To do that, we draw our diagram and determine if this is a left, right, or two-tailed test. And because we have an equality in the null, we would say it's a two-tailed test. In other words, we could get a rejection if we get a sample mean that's much higher than this or much lower than this. It could be either way. So Z alpha, our critical value, will be based on the table and 0.005 in the tails. How do we know? Because our level of significance is 0.01. We have to split that though to each tail. So 0.01 divided by 2 is 0.005. This is the same as a 99% confidence interval, right? 99% in here, right? If we go to our table, we're going to be looking for 0.995, right? Because we can start with the positive Z, and we want to find in our table the probability of getting a value up to this point. Well, that'd be 0.995 if there's only 0.005 left in the tail. So 0.995, go down here, 995. So 2.58. And it's symmetrical, so the lower tail is going to be negative 2.58. Okay, so now we've got our critical Z. Now let's do our computed Z. To find the computed Z, we take our mean cost, which was $12.75. We subtract it from our hypothesized mean of $12.50, and then we divide by the standard error. Well, the standard error is, as always, the population standard deviation, okay, divided by the square root of our sample size, and the sample is 40. Okay. If you do this, you should get 3.16. So where does that lie? Well, 3.16 is up here in our rejection region, in the upper tail. It lies beyond the 2.58 that defines that rejection region, which means we reject the null, okay, and accept the alternative. We reject the hypothesis that the population mean is 1250 and accept the alternative that it is not 1250. Simply put, this particular sample with a mean of 1275 is too far above the hypothesized mean of 1250 to be considered likely if the true population mean were 1250. Okay, so I'll pick up with the next application in the next video. Thanks.